Welcome back to my favorite universe. We spent several lectures talking about death and destruction by virtue of black holes or meteor impacts and the like. Let's take a pause from that and talk about life, what it is to be alive, and what influences around us force us to take pause in our daily routine and ask, what is our place in the universe? When I think of influences that have forced me to take pause, being an astrophysicist, I'm prone to select images of the cosmos that do this. But I'm not alone in this regard. Many people, you don't have to be an astrophysicist, have been inspired, uplifted, have been influenced in very positive ways by images that have been brought back from space, either by astronauts themselves or by telescopes placed in orbit. And that forces us to ask the question, what are the limits of our vision? And once we reach those limits, what influence does it have back on our dreams? One of the first of these powerful photographs was one taken of the Earth. Not full Earth, taken back in the 1960s. It was not a full Earth. It's a gibbous Earth, but Earth nonetheless. Earth seen from space enabled you to see clouds, large-scale weather patterns for the first time. People looked upon the continents of the world and did not see political boundaries so carefully etched on globes and maps that we buy and we learn about in civics class. The cosmic perspective is different from the political perspective. And that had an impact. At around that time, the 1960s, people viewed us as spaceship Earth. Remember distinctly the introduction of that as a phrase into common parlance, spaceship Earth. And before that image, no one thought of us as that. Here we are together, this fragile little world, in orbit around the sun, like a spaceship. This image was followed by another image that, for me, was equally as inspiring. This next one was not taken by an astronaut. It was taken by an unmanned probe in orbit around the moon. This Earthrise on the moon in all its black and white splendor. Black and white pictures, you know, they precede the color pictures, so they give you a sense of history, sort of encoded in just the fact that it's in black and white. That is the lunar landscape in the foreground, Earth in the background. On the moon has a sky, it has a horizon. It's got Earth in the sky, just the way from Earth we have the moon in the sky. It's another world. The fact that Earth in our own minds was not the only world in town. The moon was another world, a place that we might visit. And in fact, shortly thereafter, Apollo 8 became the first astronauts to leave Earth orbit and venture to the moon. They did not land on the moon, but they went in orbit around it. And the act of going into orbit afforded them the opportunity to watch Earthrise from the moon. And here, a full-color image is, in fact, the most recognizable photograph ever taken. And it's known simply as Earthrise. For me, this image is that much more compelling, that much more emotionally rich than the first image we showed of Earth just from slightly high up. Because now, it being in color, we see Earth is not just some featureless orb out there. In fact, it is richly blue. We're reminded that, by contrast, we're reminded that the surface of the moon has no water. It's got no atmosphere. It's got no weather. It's got no clouds. And there's Earth in the distance, this fragile marble, almost aglow. This image forced me to take pause, not simply as an astrophysicist, but as a human being and as a citizen of planet Earth. This march continued. In fact, the title of this lecture is Onward to the Edge. I don't know where the edge is, but we're moving onward toward it. And the act of moving onward means we pass these signposts. One of them was first leaving Earth. The next one is hanging out on the moon. What's next? The planets. We haven't sent people to the planets, but we sent our robotic emissaries. I'm okay with that, because they can take photographs just as good as an astronaut can and beam them back. You don't even have to feed the robot. You don't even have to bring the robot back. Very affordable way to do your exploring. And in the 1970s, late 1970s, early 1980s, spacecraft that had been launched in the 1970s finally reached their destinations. The Pioneer 10 and 11 space probes, Voyager 1 and 2 space probes, especially Voyager, had close encounters with Jupiter, enabling you to see the rich detail across Jupiter's surface. You thought Earth has weather. Jupiter's got weather. It's got weather bands, turbulent eddies. It's got a storm system, the Great Red Spot we call it because it's a big red spot on Jupiter's surface. That's a turbulent storm that's been raging for at least 300 years when it was discovered. 300 years ago, we passed by Saturn. Saturn, too, we see the cloud cover on Saturn, the rich texture on the surface of these orbs. All of a sudden, the planets were not just some other thing out there. They, too, became worlds in our conscience. Now, up until then, we knew planets had satellites, sure. Moons. We knew that. But they were just little dots of light. You look through the eyepiece of the telescope, it's a dot of light. When we went there, we found out that, in fact, all the action was among the moons. The terrestrial action, Jupiter's moon Io, the closest moon in orbit around Jupiter, has a volcano on it, an active volcano. In fact, it is the most active volcano in the entire solar system. It's not on a planet, it's on a moon of Jupiter. Another moon, Europa, moon of Jupiter. By the way, these moons have been discovered by Galileo. Out of respect for his efforts in this regard, we call a set of 4 moons the Galilean satellites of Jupiter. You look at Europa. Europa has a sheet of ice covering its surface. You look there now, there's certain patterns of fractures on the ice. Look there in a month, that pattern has changed, telling us that maybe there's liquid oceans beneath the ice on its surface. These are worlds. Maybe there's life there. These are no longer abstractions of an astronomy textbook. They have become extensions of our backyard. They've changed how we think about Earth simply by recognizing that we're not the only world to think about. It may be, for example, that Venus, which has a runaway greenhouse effect, it's 900 degrees Fahrenheit on Venus, hot enough to bake a pizza, a 16-inch pizza, in 9 seconds. Something went wrong on Venus. We've got a greenhouse effect going on Earth. And we got knobs we're turning, not knowing what the effect will be, the long-term effect. I don't want Earth to look like Venus. Venus is a world that I can now think about in relationship back to Earth. And these images of these planets forced me once again to take pause at our place in the cosmos, not only for me as an individual, but for Earth. And of course, given the scale of the galaxy and of the universe itself, these are worlds unnumbered. In the 1990s, another image came by. An image brought to us by the Hubble Space Telescope. The Hubble telescope, let me remind you, was the world's first orbiting observatory specializing in visible light, ordinary light that our eyes are sensitive to. It's an ordinary telescope that has been endowed with the capacity to do extraordinary things. Early, it had a bad mirror. You might have remembered this from the news. The shape didn't. We fixed that. We were able to fix it because the Hubble Space Telescope was shuttle launched. There's a problem. Oh, send up a second shuttle mission, retrieve it, fix it, put it back, and come back down. Space at its finest, actually. Going up to repair something. It's like orbit is your garage. It just felt good realizing that we could do that. It's a space-based optical observatory. We put it out in space, lifted above the atmosphere of the Earth. We've had optical telescopes for 400 years. Ever since Galileo made his telescope and looked up with it. He didn't invent it, but he was the first to look up. That was 400 years ago. What could Hubble possibly do for us that we haven't already done here on Earth? What it did for us is enabled us to see the universe without the turbulent effects of Earth's atmosphere. As light comes from the distant depths of space, it travels in a perfectly straight line. You get a sharp image. Here it is coming in. It hits the atmosphere. Uh-oh. Variations in temperature and density force that light path to become refracted, dispersed, smudged, smeared, and by the time you take a photograph of whatever that cosmic... And I can analogize this. This was a story described to me. I happen to have 20/20 vision, so I found the story fascinating for someone who has uncorrected vision. The person said they got glasses very late in life. She got glasses very... I said, well, what was the effect when you first put on a set of glasses? She said, well, she knew intellectually that lawns had blades of grass, but never actually saw blades of grass. In fact, it just looked like a carpet. You put on... And so Hubble gives us that vision. Now, the Hubble Deep Field that's the name of a single photograph taken by that telescope, which for me is more profound than any picture from the Apollo era. More so than Spaceship Earth, Earthrise, even more so than the beautiful and richly detailed images of the planets in our solar system. The Hubble Deep Field, let me tell you what that is. First of all, if you want observing time on the Hubble telescope, what you have to do is apply. You write up a proposal and you apply. And about anywhere between 2 and 10 times more requests for time are submitted than are allocated. So it's oversubscribed, it's simply called. It's an oversubscribed telescope, as are most good telescopes. Now, what do I say? I say, I want to look at this object because I think it's interesting for these reasons, and you go on and on and on and on and on. And a committee reviews it. Oh, we agree that's a good object given time. But suppose I wrote in a proposal and said, I want to pick a part of the sky completely randomly. And I want to blow 10 days of exposures on that one spot on the sky and just see what comes up. It would be laughed out of the room because there's so many other worthy proposals. People wanting to discover the nature of quasars or black holes or the spectra of gas clouds in the universe. So what this took is something called director's discretionary time. The director of every observatory, including the director of the Hubble telescope, has time that he or she can allocate on a whim. Doesn't have to go through peer review, they can just assign it according to their discretion. Maybe someone, if it's ground-based, was clouded out on one of their observing runs, and they have a special interest in that project. They give them some extra time just so that maybe it's a student who needed the time for the thesis. That's typically how the discretionary time gets allocated. This particular case, the director said, I'm going to take 10 days consecutively of the observing time of this telescope. And I'm going to select a completely random but especially boring part of the night sky. How boring is it? I don't want any bright stars there. I want it to be away from the plane of the Milky Way galaxy, because the plane is very thick with dust and gas and things that would obscure your view. I want to pick a part in the sky where Earth doesn't get in the way, because Hubble telescope is orbiting very close to the surface of the Earth. And as Hubble telescope orbits Earth, there are actually some directions it can look, where Earth, no matter where it is around the Earth, it can always look into that direction. So it found a spot continuously visible. Avoid clusters of galaxies that we already know about, because we won't be learning anything. Just find the most uninteresting part of the sky you possibly can. And they did. It's a little swatch of sky near what happens to be the Big Dipper in the northern cap. There's the North Pole of the Earth. The Big Dipper on any given night is tracing circles around the North Star, a continuously visible zone. The Hubble telescope found that one spot, took 342 consecutive exposures of the identical scene. You take all those exposures, then you add them together to make one image. Very high quality image. The amount of time allocated to this photo was larger than any other observing project ever granted by the Hubble telescope. You know how much of the sky this image represents? The field of view of the Hubble is not that large. It's not that large. And this particular picture was 1/100th the area of the full moon on the sky. 1/100th the area. To give you an idea of that, take a penny. Take a penny and hold it at arm's length and ask yourself, how big is the size of Abe Lincoln's eyeball? That is the size of the patch on the sky represented by the Hubble Deep Field. Let's take a look at that image. Here it is. That is the Hubble Deep Field, one of the most boring parts of the night sky. And what does it reveal? Thousands of galaxies. Practically every splotch of light in that image is an entire galaxy, not much unlike our own Milky Way, bearing hundreds of billions of stars each. What's extraordinary about this image is, given the precision of Hubble's imagery, you can get close to the picture and look in on the galaxy. I've seen pictures sort of like this before, taken by ground-based telescopes, and it's got just as many galaxies, but they're just all smudges. They're just smudges. And I look at it and say, okay, you get a little closer to the smudge, it's just, I'm closer to a smudge. Here, as I look real close, I can see structure. I see spiral arms. I see regions of extra star formation. I see different colors. Some galaxies are larger. They're likely closer. Other galaxies are smaller. They're likely farther away. Where does it get the colors? Why are some galaxies blue? Some stars are blue. Those galaxies are highly represented in that species of star. How about the red galaxies? Some stars are red. Some stars are white. We have red, white, and blue, and everything in between. Remember, this is the size of Abe Lincoln's eyeball on a penny held at arm's distance, projected on the background sky. So this is not simply a picture of something flat. It is a beam through the universe, looking at nearby things as well as objects that are the most distant, all compiled into one image. The farthest known galaxy in all the catalogs is in this picture. It's a red dot. Wait, how did it turn red? Well, there's this expanding universe effect. We're in an expanding universe, and light from galaxies, the wavelength of the light in an expanding universe gets stretched. If you stretch light, you give it lower and lower energy, and red light has less energy than blue light. So if you start out a blue galaxy and you're very far away in this expanding universe, receding quickly, your blue colors become red. And so the farthest galaxy in this picture is actually red. Let's see if we... Right there. We zoomed in on a little piece of the Hubble Deep Field, and that little red thing in the center there, that galaxy, we see that not as it is, but as it once was, nearly 13 billion years ago. That galaxy is one of the earliest galaxies known. Its light has been traveling for 13 billion years to reach us. And it represents it's a signpost for what the universe was like in the distant past. Once again, you can see every other smudge there is a galaxy, and just to the right of our red smudge is, you see structure in another spiral galaxy very distant. Now what we can do is, we can extrapolate our view into the Hubble Deep Field and say, suppose every patch of the sky looked like this. Then how many galaxies are there? You know, you get about 50 billion galaxies. So if you add up, you say, okay, we got several thousand here and several thousand here. You just keep doing that. You can do this statistical exercise. You get about 50 billion galaxies. Well, let me reiterate that ground-based telescopes, some much larger than the Hubble, the Keck telescope in Hawaii, is 10 meters in diameter. The Hubble telescope, about 2.5 meters in diameter. It's much bigger. It's much bigger. It has much greater collecting power. It can detect everything that Hubble detects. But it's not, if you just show me a picture of smudges and tell me they're galaxies, okay. But if I can see into their soul, if I can see what kind of galaxy it is, what color they are, what shape they take, and the knowledge that each one of those galaxies, based on ours as a representative case, contains 100 billion stars. 100 billion stars? That every point of light, except for one or two, every point of light is one of these galaxies? Just panning across the image. And as we pan, you see different galaxies go by. And I wonder, are they looking at us? Is there life on those galaxies looking back at us, asking the same question? Once again, by analogy to the planets, becoming from an abstract orbs that are out there to becoming real worlds, the Hubble Deep Field for me turned galaxies from abstract things out there in the cosmos into worlds. Once again, worlds unnumbered. Now, this area of the sky, the Hubble Deep Field, in a way has been sanctified by the Hubble telescope. And what I mean by that is people now take other kinds of telescopes and train it on that same spot on the sky to see if you can add information to it. Hubble telescope is only an optical telescope. It's looking in red, orange, yellow, green, blue, indigo, and violet light, and a little bit of ultraviolet. Let's take other kinds of telescopes and point to that same area. Do you see anything different? Combine the information. So that the race was on to find out how many extra observations we can add to it to create a total picture. A total picture. I've got an area, this same area now, taken with the Chandra X-ray telescope. As Hubble was a famous astrophysicist of the past, so too was Subrahmanyan Chandrasekhar, a famous astrophysicist, died recently as a Nobel laureate. It's a telescope named in his honor. A telescope as grand as Hubble, but specializing not in visible light, but in X-rays. Notice the scene looks very different. That's good. That tells us that X-rays are looking at something different. In fact, black holes, we learned in a previous lecture, the accretion disk that surrounds black holes and neutron stars can give off X-rays. So what we're doing now is tracking the presence of black holes. And I have no doubt that every one of these dots of light in this image is a supermassive black hole in the center of our galaxy, dining happily on gas clouds that have come too close. It tells us something different about that spot on the sky. You know, we've got a lot of unanswered questions. Do we have the right to extrapolate to the whole cosmos what happened in this one little patch of the sky? Maybe the sight line through the Big Dipper, maybe there's something bad or non-representative about that spot. So let's take another spot. And we did that. In the diametrically opposite direction. The Hubble Deep Field south. We don't expect it to look exactly the same because it's a different direction on the sky, but it looks statistically the same. You have about the same number of galaxies, about the same distribution of colors, about the same array of shapes and sizes. The analysis bears that forward. So I ask, now we've looked at two spots, do we now have the right to extrapolate to the whole sky? I'm extrapolating to the whole sky. I have no reason to believe that this side of the universe is going to look fundamentally different from that side of the universe. And we've got it in two directions. I think it'll be a waste of time to go to every single postage stamp, plus it'll take 1 billion years to do that, given how small this region is. So let's assume that. But questions still remain. This is such a beautiful view to the edge of the cosmos. I'd ask, are the laws of physics the same? Everywhere? Through all of time? In every nook and cranny? Are the laws of physics yet to be discovered that will grant me greater insight into what's going on in this image? Just as our first views of the moon. It's like, let's go there and then find out more about the moon. Our views back to Earth. We now know more about Earth for having been in space to look back to Earth than we did being on Earth looking up. So now I'm looking out to the cosmos, to the edge of the cosmos, and I want to know more about it. But occasionally I worry, are there enough laws of physics known to come to the understanding that I seek? Planets around stars, among those unnumbered galaxies, do they have life? If they have life, is that life intelligent as we define intelligence? And like I asked earlier, are they looking through their telescopes at us? Is there a Hubble Deep Field for their planet? And are we a galaxy sitting on their photograph, and they're asking the same questions we are? Or are they just looking for shelter, food, and sex, like most life forms on Earth do most of the time? I don't know. But I do know that this Hubble Deep Field for me is a window, and I think of reaching out through this window. And I reach through. Someone has actually turned it into a window spread out in 3 directions. A colleague of mine, Ken Lanzetta, took the Hubble Deep Field and took all the galaxies which are spread through time and distance and created a fly-through of the Hubble Deep Field, adding the dimension of distance to it, which makes it that much more compelling to me as an intellectual journey, as a place to gaze upon and wonder, especially since that gaze is a gaze that takes you to the edge of the cosmos. When you go out under the night sky and look up, what are you doing? You're stargazing. But when I look through this window that is the Hubble Deep Field, I galaxy gaze. I galaxy gaze through time. And in so doing, I revel in the diversity of colors and forms and shapes and structural detail exhibited in the objects of that photo. And when I do this, the boundary between my knowledge of the cosmos and my ignorance calls to me. And when I reach to the edge of the universe through the Hubble Deep Field, I do so knowing that along some paths of cosmic discovery, There are times when, at least for now, one must be content to love the questions themselves.